Okay, this is our test on complex numbers or polars, complex numbers, and vectors. Okay, so I've got the test here to the left, and the first task we were supposed to do was to plot some points on the grid. I've got a large grid here. We note that A was already plotted for us, so we don't need that. B is 0, -7. We count down 1, 2, 3, 4, 5, 6, 7. So this is point B. So point B in XY world is 0, -7. That was given. So we plotted that. Now we just need the R and the theta. Obviously, we're on the 7th ring. We counted out 7 rings to here. And the theta will go -π/2. You could do -90 degrees if you want. Okay, C was given as 6π/4. And we just have to plot that. So it's on the 6th ring at a 45-degree angle. Here's our 45-degree angle here. So we just go 1, 2, 3, 4, 5, 6. And there's our point C. And so we need the R and the theta. We do know that X is our cosine theta. So X is 6 times the cosine of π/4, which is 6 square roots of 2/2. And yes, that can be reduced. Y is our sine theta. So 6 square roots of 2/2. And if you want to reduce that, that's fine. Obviously, this will be 3√2, 3√2. Okay, point D. Point D is given in XY as -3 square roots of 3, 3. And the task is to find the R and the theta. These are a little bit more interesting. We do know that R is square root of x squared plus y squared. So R can be square root of 9 times 3 plus 9 square root of 36, which is 6. So R is 6. And then we just need to figure out the theta value. Let me stop this, pause it for a second. Okay, we're back again. And I believe we're recording here. It says recording, so I think we're okay. Let's see, we need to figure out what theta is. Theta is the tan inverse of y/x. That was a nice formula that we got. So that's going to be the tan inverse of y, which is 3 over minus 3 square roots of 3, or if you want, the tan inverse of -1 over the square root of 3. So assuming that's a standard angle, because the directions do say we want exact values here, right? Exact values. The implication there is that we want to have a particular standard angle over here. Okay, we do know that this shows that we're in quadrant 2, right? X is negative, Y is positive, so we're up here. And in fact, we could probably take our calculator and sort of guesstimate where this might be. The calculator pretty easily can show the X value as negative 3, I'm turning on my calculator here, -3√3. Okay, so that's about -5.2. So you can think this is about -5.2 and then 3. So if we're just looking at our grid, we can sort of suspect, let's see, -5.2 and 3, 1, 2, 3, 4, 5 and a little bit, and 3, 1, 2, 3. It looks like we're going to be right about there. And that is, in fact, going to be the point D. And if we just went that approach, then it's pretty clear that the angle is 5π/6. If you wanted to go this route, you could also do that on your calculator. The tan inverse of -1 over the square root of 3, tan inverse of -1 divided by the square root of 3. and you'll get that. And if you just, this is now in radians. If we just double check and see if this is the same as 5 pi over 6, 5 pi divided by 6, you go, oh, okay, not quite the same. What's happening there? You do need to remember from earlier in the course that the tan inverse only returns values in the, don't know why this keeps popping up. Sorry about that. Tan inverse only returns values over here in quadrants 1 and 2, and we do need, or quadrants 1 and 4, and we do need to be in quadrant 2. So my suspicion is that tan inverse is giving us this angle. If you wanted to use that, you could. You could also have, so -6 and -pi by 6. So this is an alternate solution for D. D is actually the hardest problem on that set. Okay, and let's go ahead and finish off E. And okay, so E is got our theta coordinates. This just keeps jumping on me. As 8 and 5 pi over 4, 8 and 5 pi over 4. So not too terribly hard to plot. 5 pi over 4 is right here. This. Okay, I'm going to have to try to figure out what's going on here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's point E. And again, the XY is very similar. We know X is R cosine of theta, 5 pi over 4. That's a standard angle. So 8 times -square root of 2 over 2. That's going to be our X coordinate. Or cleaning that up if you want. -4 square roots of 2. And the Y coordinate is 8 times the sine of 5 pi over 4, which is also -square root of 2 over 2. So -4 square roots of 2. So there's your XY for E. Okay, so a little time consuming to plot those out. But let's see if we can go ahead and knock out the rest of these much more efficiently. Okay, point C, this guy right here, point C, let me pull up a new screen. Point C, we had given as polar coordinates of, let's see, r theta. That was given as 6 pi over 4. And we had calculated the xy's. And the xy's we calculated as 3 square roots of 2, 3 square roots of 2. And for problem number 2, it says you had to write that as a complex number. So either a plus bi, or in trig form as the r cis theta. That's our trig shorthand notation. So either one of these would work. If you wanted to do the polar form, the trig form, you just write 6 cis pi over 4 and you're done. If you wanted to do the rectangular form, you would have needed to know these rectangular coordinates. So assuming we got that right, 3 square roots of 2 plus 3 square roots of 2i. Right, so the same point can be represented as a complex number. Okay, 3, write the vector that has a terminal point as C. So once again, we're still dealing with C. Now we're looking at this vector that starts from the pole and goes to C. And we want to write this either in component form, AB, or in IJ form using the unit vectors, IJ form. So our vector V is going to have our rectangular coordinates, 3 square roots of 2, comma, 3 square roots of 2. So you can do that. Or if you want, you can do 3 square roots of 2 times, the little unit vector, and 3 square roots of 2 times the unit vector j. And again, just don't, the caution, of course, is this unit vector has absolutely nothing to do with that. This is the imaginary number. This is the little unit vector 1, 0. Okay, so that's the first page. Second page. Now we have, let's see, we have this cardioid. We have some points labeled on the cardioid, and our task is to find the x and y coordinates. So let's see, point A is labeled over here, and just counting rings, we see this is 2 rings over and 0 degrees. So A in XY world would just be 2, 0, And in our theta world, the coordinates are exactly the same, 2, 0. Points on the polar axis and on the x-axis have the same ordered pair. So that one's easy. Okay, C looks like probably the next easiest because it's straight down, 1, 2, 3, 4 down. So this is the ordered pair 0, 4 in XY world, 0, 4. And again, because it's 90 degrees down, it's not hard. R is 4, and you can do negative pi over 2. If you wanted to run around in a positive direction, you could do that as well. But there's C. And a B looks like the tricky one. Now it is on a standard angle there. So we've got the theta, 5, that's not 45 degrees, so that's 7 pi over 6. 7 pi over 6, just looking at counting. This is 15, this is 30 degrees below. Okay, so 7 pi over 6. And on the ring, 1, 2, 3, it's on the third ring. So there's our r theta. And then once again, we need to go back. X is r cosine theta, and y is r sine theta. So x is going to be 3 times the cosine of 7 pi over 6. Again, this is a standard number. You should know that. So 3 times negative square root of 3 over 2. And then the y coordinate is 3 times the sine of 7 pi over 6. So 3 times negative 1/2, negative 3/2. Okay, so that takes care of the cardioid. Now use your calculator in polar mode to see if we can come up with the graph of r is equal to negative 4 cosecant theta. Okay, so the first thing we'll do is we'll put it in polar mode because we're supposed to do r equals. And we get r is equal to negative 4. Now, there is no cosecant button, but the problem does say that recall that cosecant is just 1 over the sine. So we can just divide this by the sine of theta. And here it is in the standard window. Appears to be a horizontal line at negative 4. So on our test, we would just go down 1, 2, 3, 4, and draw this horizontal line. And we're done with that. Now, the question is, what's the rectangular equation? Well, you might suspect that this is y is negative 4. I mean, if you just wrote that down guessing horizontal line at negative 4, you'd be right. But why does that make sense? We know that r is negative 4 cosecant theta, or if you want, r is negative 4 divided by sine theta, or if you want, r sine theta is negative 4, and recall that y is r sine theta. Okay, so it makes sense this is y is negative 4. Okay, so that takes care of that one. Let's see, again, use your calculator to graph this polar, now this says it's a 4-leaf rose. So we're in polar coordinates. The equation is given to us as 5 times the sine of 2 theta. So we just put that in there, 2 theta, and we hit graph, zoom 6. So yeah, sure enough, we get this polar curve. Now we might want to square this up a little bit to make it look a little bit prettier. And as we trace along here, if we just sort of try to see, because the problem did say, try to be very particular about where the tips of the leaves are. Okay. Okay, so it looks like as we go out there, the theta value at 45 degrees, right there, has both x and y as 3.5. So let me just note that. If theta is 45 degrees, x and y are both 3.5-ish. So you might want to suspect that there's, let me pull up a new screen here. We get r is 5 sine 2 theta. So theta is 45 degrees. R is going to be 5 times the sine of 90 degrees. And we know the sine of 90 degrees is 1, so r is 5. So sure enough, this point, let's see if we can find this point all the way at the end here, is at ring 5. The 5 in the equation sort of leads us to that. So what I would do to look at this thing and make sure you go out to the 5th ring, 1, 2, 3, 4, 5. And that's going to be true in all of these. So put your rose petal curves, if you will, on the 5th ring, and then draw your little rose curve. Just try to duplicate as best you can off the calculator. And that would be fine for that one. Okay, so there's all the polar stuff. Now the rest of this test dealt with complex numbers and graphing and such. I don't think we need our calculator anymore. Okay, so question 5, it says Z is 12 minus 5I. The task was to sketch that. So 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 1, 2, 3, 4, 5. So here we are. This is 12 minus 5I, done. And the second part says, what's the absolute value of that? Well, remember, absolute value is just distance away from the origin. So we have this little triangle here, and this is one of our Pythagorean triples from geometry, 5, 12, 13. So sure enough, the absolute value of Z is 13. Now, if you don't recognize the 5, 12, 13 triangle, and you had to write the square root of 12 squared plus 5 squared, square root of 144 plus 25, square root of 169, square root of 169 is 13. But shame on you if you don't recognize that from geometry. Okay, let's see. Convert the complex number. This is problem number 6. Convert the complex number. We've got Z is 10 cosine of pi over 4 plus I 10 sine pi over 4. Now, this is only worth a point, and you should know the cosine of pi over 4 is square root of 2 over 2. So 10 square roots of 2 over 2 plus 10 square roots of 2 over 2, and we should probably move the I there. Okay, so we're done with that. 5 root 2 plus 5 root 2I. That was only worth a point, not a lot of time to do. Dumois says, can you actually raise that to the 4th power? Because we have this in cis form, this is the bonus if you want. You take 10 to the 4th power, that's 10,000. You still have your polar form there, and now you take pi over 4 and multiply that times 4. Okay, so 4 times pi over 4. Okay, so this would be 10,000 cis of pi, and that doesn't look terribly hard to do if you wanted to do the bonus. Okay, so now we've got some vectors. I need to make this a little bit larger so I can see it. Let's see. Write the vector 12, negative 5 in ij form. We can do that right here. This is, oops. This is the vector. Where did my problem go? Okay, so this is 12i minus 5j. Done. Magnitude, again, it's really the same problem that we did on the previous page. That's 13. Cartesian point in the xy plane with 0.05. Let's see if we can find that. Okay, 0.5. This is awkward. Can be expressed as one number in the complex plane. What number is it? You can give it either in a plus bi rectangular form. Where are we? A plus bi rectangular form, or in polar form, and then what's the absolute value? So this is xy plane 0.5. 1, 2, 3, 4, 5. There we are. What number is that in the complex plane? That would be 5i. Or if you want 0 plus 5i, or if you want it in cis form, you can say 5 cis pi over 2. All of those would be equivalent. Okay? So that ordered pair, that point in the xy plane, is the same as the point 5i in the complex plane. Okay, what else did we have to do with this? Oh, absolute value. Okay, so the absolute value of 5i is just 5. Just how far away from the origin, so that's fairly quick. Okay. Number 9, the point, the polar point, polar R theta plane. And it says we have 5, 90 degrees. Well, lo and behold, that's exactly the same point we were just working with, so it's the same problem. Can be the terminal point of a vector. So let's draw a vector from here and going up to there. And now it says call the vector A and write it in component form. So 0 in the x direction and 5 in the y direction. So there's our vector A. Or if you want, you could write it in ij form. So 0i, don't need that obviously, plus 5j. And what is the magnitude of the vector? We already did that. That's the length. That's 5. Okay, so these two, or these three problems look like we're all dealing with adding, subtracting, and dot products. And I'll do that over here. So let's see. This keeps jumping on me. Sorry about that. Okay, so we have vector v, 2, 3. Vector, or sorry, 2, 5. Vector w is negative 2, 3. 2, 5, and vector w is negative 2, 3, and our task was to find v plus w, just add up the components, 0, 8. We're supposed to find v minus w, subtract the components, so 2 minus a minus 2 is 2 plus 2, and 5 minus 3 is 2. And lastly, the dot product, which I generally like to write these down so I don't have to chase around. This is 2, 5 dotted with negative 2, 3. So we multiply these, that's negative 4, and we multiply these, that's 15. So we get 11. That's the dot product. Okay, last page of the test. Oh, we're on the last page of the test. Okay, so, oh no, here we are. So the same two vectors, plot the vectors and find the angle between them. Okay, so maybe we can just scroll down here. We have these two vectors, 2, 5, and negative 2, 3. 1, 2, 1, 2, 3, 4, 5. There's vector v, and negative 2, 3. There's vector w. And our task is to find the angle between. We know the cosine is the dot product divided by the product of their magnitudes, their lengths, if you will. So we get 11 divided by, now, how long is v? Good old Pythagorean problem. This is 2, this is 5, square root of 29. Right, and how long is w? Again, Pythagorean theorem, geometry. So this is 2 and 3, so we have square root of 4 plus 9 is 13. Okay, so to find the angle, again, I would grab my calculator and just dump those in there. For this one, I'll go to degree mode. I like to think in degrees, but if you want to do it in radians, that's perfectly okay. So cosine inverse of 11 divided by square root of 29 times 13. Okay, so 55 degrees, 55, 491. So theta, and this is the cosine of theta. So theta is 55.491 degrees. Okay, what's the next thing? Get my calculator down, find my question. Okay, so we're finding, again, orthogonal vectors, which means their dot product has to be 0. Okay, so we have 3, 1, 2, dotted with 1, 3, C has to be 0. We know that because they're orthogonal. So 3 plus 3 plus 2C has to be 0. 2C, 2c, Joe. It's been a long day. 2c has got to be negative 6. C has got to be negative 3. Okay, so that serves that one. And the last one has to do with these cross products. So we have 3, 1, negative 2 crossed with 1, 3, 5. We have to find the cross product and then show that the cross product is orthogonal to both of these. Now, on the review video, we did it using the rule of Saris, which I don't particularly like, but I know a lot of Algebra 2 students like it. So we'll go ahead and do that here. Remember, the rule of Saris says you're going to take that column and rewrite it again, and take this column and rewrite it again, and then go ahead and find the diagonal products. So we're going to go to the right, multiply these guys together, that's 5i. Multiply these guys together, minus 2j, and multiply these guys together, that's plus 9k. And then on the other diagonal, these are the ones that are going to be subtracted. So we have 1k, and this is minus 6i, and then plus 15j. So, and again, we did this one on the review, so you can just refer back to that if you want. We have 5i minus 2j plus 9k, and you're subtracting off this other product, k minus 6i plus 15j. Just sort of keep your wits about you. 5i take away a negative 6i is 11i. Minus 2j take away 15j is minus 17j. And 9k take away a k is 8k. So there's our cross product in ijk form. I'm going to write it in component form just because I don't like the i's and the j's and the k's. And 8. Okay, so I think we're all good there. Now the check, of course, is to see whether or not the dot product is 0. So we should dot this with the cross product and expect to get 0. 3, 1, negative 2, dotted with 11, negative 17, 8, will be 33, minus 17, minus 16 is 0, sure enough. And the second one, we've got 1, 3, 5, dotted with 11, negative 17, 8 is supposed to be 0. So let's see, 1 by 11, get rid of this over here, get some room. 1 by 11 is 11, 3 by negative 17 is negative 54, and 5 by 8 is plus 40, and sure enough, that adds up to 0. Okay, so there's your checks. And was there anything else? I think there was a bonus way down at the bottom. Find the angle between these two vectors. Sort of hard to sketch, but we know the cosine of the angle is going to be their dot product. Let's see, so we have 3 plus 3 minus 10 dot product. Remember, multiply, multiply, multiply. So 10, and the product of their magnitudes. This first one, grab another pen. We've got 9, 1, and 4. So 9, 1, and 4 is the square root of 14. And the magnitude of the other guy, we've got 1, 9, and 25, so that's square root of 35. And so theta is the cosine inverse of whatever number this is. This again screams calculator. We've got negative 4 over the square root of 14 times 35. Okay, so let's see. I'm in degree mode, so that will give it to me. We just need cosine inverse of negative 4 divided by root 14 times 35. Okay, so 100 degrees, approximately, round to the nearest thousandth. 100.411 degrees. And of course, that could have been in radians. I mean, if you were in radian mode, that's perfectly acceptable. The problem didn't say to do it in degree mode. So if you said theta was 1.752, that would also be acceptable. Okay, so there's your polar and complex number and trig test. Let me go ahead and stop this.